Welcome back to the AI Research Roundup. I'm your host, Alex. Today is May 5th, 2025, and we're diving into an interesting ICLR conference paper published just over 3 months ago, titled Attention as a Hypernetwork. Alright, so this paper basically reframes multi-head attention, suggesting it works like a hypernetwork. This structure, they argue, is crucial for compositional generalization, letting models handle new mixes of familiar ideas they've learned. So to visualize this, the authors provide a helpful figure. It basically breaks down how multi-head attention can be viewed as a hypernetwork. First, it shows a generic linear hypernetwork, where a latent code generates parameters for a value network. Then, it illustrates how attention scores across different heads for a key query pair actually act as this latent code. Finally, it puts it all together, showing the equivalence between standard multi-head attention and this specific hypernetwork structure. Alright, so moving to the empirical side, this figure from page 5 dives into a fuzzy logic task to test these ideas. Okay, it compares their proposed Hypernetwork attention, that's the one designed to strengthen the hypernetwork mechanism, against standard linear and softmax attention. We see Hypernetwork performs much better on out-of-distribution examples, especially as the tasks get harder. And those plots on the right visualize the latent code, showing it clusters meaningfully, which supports the hypernetwork interpretation. Okay, building on that abstract reasoning theme, this next figure introduces another task they designed called SRAVEN. It's basically a symbolic version of Raven's progressive matrices. So the figure details how these SRAVEN tasks are constructed, using different rules, combinations, and importantly, how they create train versus out-of-distribution splits. It's another way to really push the model's ability to generalize to unseen rule combinations, testing that compositional generalization idea again. Okay, so this figure shows the results on that SRAVEN task we just talked about, specifically focusing on how scaling affects performance. Alright, Part A looks at increasing model width, while Part B looks at increasing depth. Across both, and as the number of training tasks increases, we see that HILA, the pink line, consistently achieves better out-of-distribution accuracy compared to standard softmax and linear attention. It really highlights how scaling improves compositional generalization, especially with the HILA approach. Alright, so digging deeper into those SRAVEN results, this figure really dissects the hypernetwork aspect. Okay, parts A and B visualize the latent codes, showing that HILA tends to create more distinct clusters based on the task roles compared to the other attention types. Then, parts C and D show that multiple attention heads are indeed beneficial for OOD accuracy, and disrupting this, like reducing features, hurts HILA more, supporting that hypernetwork mechanism idea. Okay, so to make this HILA approach more concrete, this figure from the appendix actually shows the pseudocode side by side with standard softmax attention. Alright, you can see the key differences highlighted. Instead of softmax, the HILA uses RMS normalization across the heads. That's line 6. And it adds a ReLU nonlinearity in the value processing. Line 9. These are the architectural tweaks designed to strengthen that hypernetwork structure we've seen helps generalization in those SRAVEN tasks. Okay, so building on that pseudocode, this table really puts those architectural choices to the test with an ablation study. Alright, it compares standard softmax, linear, and HILA attention on the fuzzy logic and SRAVEN OOD tasks. Well, you can see HILA consistently performs best. And importantly, removing its key components like RMS head or the nonlinearity generally hurts performance, while adding them to linear attention doesn't fully bridge the gap. This really supports their design. Okay, so wrapping up our discussion, the big picture here is that viewing multi-head attention as a hypernetwork offers a compelling explanation for compositional generalization in transformers. Alright, the results show that the latent codes formed by attention heads capture task structure, and strengthening this via HILA really boosts performance, especially on those tricky OOD reasoning tasks. That's our roundup for today. Thanks for joining me.